That was hard. But okay, so any questions on the practice quiz? No? Okay.
Yeah, I have a question.
Okay, go ahead.
Oh,
So on question 5 for the solution, he selected z first. So he set z to 1, and then he selected the other values. Can you do that, or do you need to select values from left to right?
Wait, which one is question 5? Sorry.
It's
Let me see. Question 5. Okay, so that's 7. So this one is question 5. Can you see my screen right now? Determine whether the following.
Yeah.
Determine whether. So what was your question?
So in the textbook, it brought up an example of how switching the order of declaring the variables would change the outcome. And so on this one, they said you need to read it from left to right, but in the example, he selected z first, even though it's defined later on. Is that okay to select z first and then select the other two variables after that?
Yes, the thing is that it's just, so for this problem specifically, it determine whether the following quantified predicate is true or false. So the thing is that we have z here, right? So you want something that's less than z. So the thing is that you want z to be as small as possible. You want this side of the equation to be as small as possible. That's why he chose 1 as z. Does that make sense? So like
Sorry, would it make any difference if you put z first before the other two variables? Because it brought up that point in the textbook where the order in which the variables are declared changes things. And I just don't quite understand what the textbook was meaning by that.
I don't think it matters. You can choose whatever counterexample. So like you mean that, so choosing x first would change the outcome of this equation. That's what you think? That's what you're saying?
Well, writing z last would change the outcome instead if it was written first.
Written first in what way? Like you mean like z, so if I write z squared is greater than x squared plus y squared?
No, by writing all of values z within subset A first, and then the x and y. Because right now it's written, there exists an x value within A and a y value within A, and then z is the third one. But would it change things if z was written first and then?
So you mean it's written for all z in A like this?
Mm-hmm. Because there was an example that dealt with that, and I didn't quite understand that in the textbook.
Yes, I'm pretty sure this would change how you would interpret the sentence itself. Like if you switch the order, Nancy, is that correct?
yeah, I think so.
Yeah, so if you switch the orders, okay, somebody asking where in the textbook is that? Do you remember where in the textbook that is? But this, so like I am like pretty sure if you change the orders of the predicate, that would mean something differently. Like the orders of the predicates does matter.
Yeah, so I guess that's kind of what I assumed, but he selected z first and then the other two variables.
Yeah, but that doesn't mean that he's changing the order of the sentence. He didn't change the order of the statement. The statement is still the same statement. There exists x, y for all z. So because we're saying for all z, right? For all z, x squared plus y squared is less than z squared. So it doesn't matter which z you choose. If you can find one z that makes the statement false, the statement is false, right? Because it's for all z. If you say that if this statement becomes for all x, y, there exists z, blah, 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 then you cannot choose one z because it just says there exists, right? So this statement specifically, he chose z is equal to 1 in the answer key is because the statement here is for all z. Like the order shouldn't change. He didn't, choosing z is equal to 1 first didn't change the order of the sentence.
Okay.
Yeah, it's just because he's giving, like in this case specifically for all z in A, if you can find one z that makes the statement false, that is the counterexample that you want to be giving.
That works. Thanks.
No problem. Somebody asking, so you can, wait, any of the three values for any variable, regardless of the order that you list, A is equal to. So if you want to give an example, you can choose whichever one to give a value first. So like if you want to try to find a counterexample, you can assign z first and then x or y, or you can assign x or y first and then z. Like that doesn't change how like that doesn't change the example itself. So many questions. Okay, so can we go through question 5 in its entirety? Sure, let's do that. So so we have, okay, 1 second. So we have this statement right here. There exists x in A, y in A for all z in A, x squared plus y squared is less than z. So we don't know if this statement is true or false, right? But then we see that all of these values are first of all positive. So 1, 2, and 3, right? All of them are positive. And then if the statement would be false, the right side is as small as possible. So the right side, if the statement is false, then we can assign z to be something as small as possible. So let's say let z equal to 1, then we have x squared plus y squared would be less than 1. Right? We just plugged in z is equal to 1. So in order for this statement to be true, we have to have some x and y both in A that make this statement true. Is that possible? We can think about it like, if x is 1, so let's just make them as small as possible. X is 1, y is 1. These are the smallest possible numbers that you can get. 1 squared plus 1 squared, that's still 2. That is definitely not less than 1. And that is the counterexample that we need. So basically 1z is equal to 1. That is the counterexample. All right, any other question from the practice quiz?
Yeah, number 7, please.
Okay, let's go to number 7. Negate the quantified predicate and determine whether the original statement or its negation is true.
So I was thinking there should be I was thinking both of them should be true, the original and the negation.
So that is not possible because think about it. If P is true, not P has to be false. You can't have P and not P, like, okay. You can't have P and not P. Like this is a contradiction. Like this is always false.
So how do you know so how did we know the original one is true? I'm just asking.
Okay, so let's see, for all x in Z, there exists Y in Z such that X. How do we know that the original is true? So, okay, so we have X plus Y is equal to 10, right? So that means X, okay, let's write, what? Oh my God. Always having trouble with this. But okay, X plus Y is 10. Let's write Y is equal to 10 minus X, right? We just subtracted X on both sides.
Sure.
Right? Okay. So then for all, if the statement says for all X in Z, there exists Y in Z such that the statement is true, right? So we now establish that these two statements are equivalent. So then no matter what we plug in as X, so we're saying for all X in Z, no matter what statement we plug in as X, we will always find a Y based on this equation. And because of closure, by closure of Z integers, Y will always be in Z. So we can always find a Y no matter what we plug in as X. Does that make sense?
Yeah, thanks.
Any other questions on the practice quiz?
Yeah, sorry, could we go back to 5? Could we talk about how it would change if we were to change the order of those, the way they're written? How that would change the problem?
For all Z in A, there exists there exists X in A, there exists Y in A. Okay, so if we change the order,
I guess that probably the more important thing is the difference between for every and there exist. So I guess the textbook, why they choose Z first is because Z is like for every Z. If you change that to there exists Z belongs to A, they have to choose X first and then Y and then Z. It's only because of the for every Z, which means it should work for 1, 2, 3. Like, yeah. Does that like make sense?
Yeah, yeah.
so I don't know if it changes the meaning of this statement, but there are certain times that I have seen there have been, like, I think there was like a homework problem or something that during my office hours, someone came to ask the question, like, how does this change the meaning if we change the order? And that for that one specifically, I remember that it did change the meaning of the statement, just like how it read in general. And that made a difference on how we were solving the problems.
Yeah, but I feel like for like we should always choose like for every whatever variable is in A first. So if there is a variable that says for every, we should always choose that first. And then we can consider the order, like if that's the first in first place or second place.
Cool.
Yeah, that works. Thank you.
Okay. There are no more questions on the quiz problems. I want to go over a proof by cases. Proof. Oh, there is one. So I'm wondering why the negation isn't true for problem 7. Okay, so for problem 7, the negation would be there exists x in z such that for all y in z, x plus y is not equal to 10. But this is just what this is like the exact same thing as we just explained. Like nothing changed. You can always find, so you can always, so whatever y you have in this case, you can always find an x that like there doesn't.
Yeah, I think that's.
This is the same statement as, like, this is the same reasoning as the one that we gave before.
Yeah.
Yeah, that was what got me confused. That's why I asked.
Or how is the like solution explained about this?
Because I thought both of them were.
I think that's where reading it from left to right comes in, because there's not an x that for every y it won't equal 10.
There exists x such that for all y, x plus y is not 10.
Right, because there's always going to be a y that it with any given x it will equal 10.
So with it saying that, sorry. So with it saying that the exists an x first, that means there is one specific x for every single y.
Right.
Yes.
So yeah. So pick an x first, and then if you test it against every y, it's not true for every y. Like there'll be one y. Yeah.
Yes.
Yeah.
There will always be one y.
Yeah, and page 48 in the textbook, it says that they need to be assigned left to right.
Yes, and then this is, I think this is like very similar to the question that the student asked during my office hour, is that when you have statements like this, you have to choose an x first and then think about all the possible y's that you have. And then if there's one y that satisfies this condition, and there is one y that satisfies this condition, and this statement is false.
Is that like how the textbook is explaining about this? Because I still feel like, I don't know.
Don't know what the textbook said, so
Okay.
yeah. So if anyone know where the textbook talked about this, we can.
There was an example problem with this kind of thing on page 48 of the textbook.
Okay.
And it talked about how changing the order changed how you would go about solving it.
Nancy, do you want to go look that up really quick if you have the textbook? Okay. I think I want to talk about this one before we go over anything else, because this will help you on the homework and probably some quiz problems as well. So this is a proof by cases problem. If n is an integer not divisible by 5, then n has a square that is of either the form 5k plus 1 or 5k plus 4. What do we think? How do we approach this problem? Any idea? You can type in the chat room or raise your hand. Go ahead.
Yeah, I think we can start by like n equal to like 5k plus 3 or something like that. Just anything with the remainder, and solve to see if we
Yeah, that is a good idea. But first of all, let's think about how many cases are there? How many cases are there for this problem?
Yeah, 2 cases. Yeah.
2 cases? Why 2 cases?
Because of 5k plus 1, and there's 5k plus 1 and there's 5k plus 2. That's why.
Well, no, n is either odd or n is even, right? There's only 2 options what n could be.
We have here 5 cases is close, but not exactly, because we have, if n is an integer not divisible by 5, right? So that means n mod.
Oh yeah, it's 4 cases. Yeah, it's 4.
Yes, it would be 4 cases, actually. So we would have n, so n not divisible by 5. I don't know why, who's the one that's figured it out? Okay, that's better. Yeah, so then then the remainder has to be 1, 2, 3, or 4, right? So basically we're saying n is 1 mod 5, or n is 2 mod 5, or n is 3 mod 5, or n is 4 mod 5. These are the 4 cases we need to consider. So normally when you're thinking about, like, when they say that an integer is not divisible by something, so if it's not divisible by 6, then we have 5 cases. Like every time we see a number like this, we need to consider all the other possible remainders. So when an integer is divisible by 5, we have n is equivalent to 0 mod 5. So this is the case where n is divisible by 5, and then we don't consider it because it says if n is an integer not divisible by 5. So now we have 4 cases, and then let's consider case 1, where n is 1 mod 5, which means what? So n is 1 mod 5, so this means what? How can we write n? Any answer?
N is equal to 5k plus 1.
Yes, so that means there exists, let's not use k, let's use something else. So that means that there exists some q in z such that, okay, I'm just gonna write such that n is equal to 5q plus 1. Okay, we're not gonna use k for now, we're gonna use like something else, and then we'll look at what happens later on. So then we have this, and then it says, then n has a square that is of either the form this or this, right? So we want n squared. So n squared is equal to 5q plus 1 squared. And open the parentheses, we get 25q squared plus 10q plus 1. Is that right? All right, so then we want n squared to be in the form of 5k plus something, right? So then we're going to factor out a 5. So we have 5q squared plus 2q. And then we have this one. So by closure of integers, this is also in Z, right? So then if we let k equal to 5q squared plus 2q, then n squared can be represented as 5k plus 1. Right? So that's case 1. Why is n equal to 5q plus 1? There's a question in the chat. Okay, so we're saying that, so this is by the division theorem, I can't remember what where it is in the book, but they talked about the division theorem. So if you think about it, we're saying that the remainder, so this number divided by 5 has some kind of answer with a remainder of 1. That's what we're saying with this n is equal to 1 mod 5. So when this number is divided by 5, there is a remainder of 1. So then you can imagine, let's say this thing is q. Then we have n is equal to 5q plus 1. So if we keep going for case 2, where n is 2 mod 5. So that means n is equal to 5q plus 2 now, because the remainder is 2. And then we can do the same thing. N squared is equal to 5q plus 2 squared, 25q squared plus 20q plus 4. So we still want something that looks like this. One of these, right? So we still have to do the same thing. We factor out of 5. And we get 5q squared plus 4q plus 4. Still using the same thing by closure of, oh, actually, this is by closure of multiplication and addition. Multiplication plus addition. In integers. So we can let this equal to k, and then we get 5k plus 4. So this is the second case. And then we keep going, case 3. N is now equal to 5q plus 3. Does anyone want to do this?
I think there's a question asking why is it n equals 2 mod 5 and not n mod 5 equals 2?
That's the same thing. There's no difference between the two. You can write either way. So mod can be like an operation type of thing. So it's like dividing. So when you say n mod 5 is equal to 2, this is kind of the same thing as like n, like this signed mod, I guess, remainder, whatever you call it, is equal to 2. It's like an operation. There's no difference. You can write whichever and it will be correct. Anyone want to continue with this? With case 3? Any volunteers? Why don't we clarify q is integer? Yes, q is an integer. I did clarify at the beginning, but like you can write this every time. So we're saying that there exists q in the integer such that n is equal to 5q plus 3. Yes, q is an integer. Q has to be an integer. Yes, we have an answer. Okay, n squared is equal to 5q plus 3 squared, and that is 25q squared plus 30q plus 9. Yes, very good. Do we have to use a different variable instead of k for the second case? So you want it to be this form, right? So like a variable is just a representation for something. Is there a certain rule? Nancy, do you know if there's like a rule? Like does it have to be unique or something? Or when is it that we can use them the same way?
I think that's fine. if you just let it equal to k. But if you let that equal to m or other variables, it's also work. It's also like fine.
Right. Okay. So then basically you're saying that this can be like 5m plus 4 if you let this to be m, and that's fine too. You just need something that looks like these two things, and the variable can change.
Yeah.
It can really be anything. Yes. Yeah. And somebody just added in the chat. Very good. 25q squared plus 30q plus 5 plus 4. Yes. That is a very good observation. And then we take the 5 out. 5q squared plus 6q plus 1 plus 4. And still, by closure and multiplication, we can let this be. Let's still do k, and then this would be 5k plus 4. So we get our third case. Very nice. And then case 4. There exists q in z such that n is equal to 5q plus 4. Our last case, n squared is equal to 5q plus 4 squared. Any volunteers for this one? Wait, somebody asking, wait, we can separate the 9 to 5 plus 4. I mean, you can split up integers however you want, as long as they add up to the same thing, right? Like you can split the 9 to 1 plus 8 if you want, but that doesn't help us really. What we want is to have this form, right? So the goal is 5k plus 4 or 5k plus 1, whichever. Like that's the goal. So in order to get that goal, we're trying to get this 4 to be left out, or a 1 to be left out. So that's why we split up the integer at the end, so then we can get all of these to be factored inside of the parentheses, and then we have this 4 left outside. Yeah, okay. So somebody wrote answers 25q squared plus 40q plus 15 plus 1. Yes, that's very good. Split up the integers to 15 plus 1. And then now we factor out 5 again. 5q squared plus 8q plus 3. And then we have this 1. And then right here, we can let it equal to k again by closure of multiplication and addition in integers. And then we get 5k plus 1. So then we covered all the cases, all the possible integers, and then we still get 5k plus 1 or 5k plus 4 for every single case. And that is how we proved the statement. So QED, you can write a little, I mean, I don't actually know a lot of people who actually write QED at the end of the proof. Some people do draw a little square like this to say that's like the end of the proof. If you want to make like your own little symbols for finishing a proof, that's fine too. I know professors before that have written like W5 as the end of the proof because that stands for which was what we wanted or something. So any questions? No question. Awesome. Okay, so any questions about anything else? Lectures, recitations, anything? We have some more exercises that we can go over before to prepare for the first quiz, or any other logistical questions on how to submit on Gradescope or whatever. Okay, let's do some more problems together. Right, the negation of the following statement is simplified to the point where there's no not symbol occurs to the left of the quantifier. Any volunteers?
There's a
Wait,
question.
can we go over? Yeah, can we go over submission process on Gradescope? I have a few questions, problems yesterday while submitting. Any specific submission problems that you would like to ask about? You can unmute yourself. The base, wait. Oh, mic doesn't work. Okay, so you just need to submit a PDF file or a set of images, whichever one that you prefer to do. I think PDF is the preferred one for us. Nancy, have you used Gradescope before? If you have more experience, you can talk about it.
Yes, I did. Like which step in the process, like, or you have problem with? Because I guess it's just like two-way. If you upload the image and you can like pick question, like for each question you can like pick multiple images, I think, or just use like the entire PDF file.
Right, and then you need to submit the 3 things. The first thing is the pledge. You can just sign it on a piece of paper. You don't have to actually print it out. You can just acknowledge, write down that you acknowledge the pledge and then you sign it on a piece of paper, and that would be fine. And then you need to submit your index card. And if you don't have an index card, you didn't make one, Bay clarified that just submit a placeholder and say that I did not make an index card or something. And then the actual problem set. It says 1 problem per, yes, you can submit multiple pages. Like you can submit multiple pages for 1 problem. It's just that we would like.
Yeah, you can, yeah.
Yeah, we just would like the problems to be separated. If 1 problem is more than 1 page, then submit both pages for 3 pages or however many pages you have for that 1 problem for that problem on Gradescope.
But I think it's actually fine, like when we're grading them, so it's not like that huge problem. So yeah.
Somebody asked, can we go over a homework question? If my index card is digital, can I just submit the digital version, or do I need to submit the printed version, like a scanned or printed copy? Digital version is fine, as long as it's legible. It's fine. There exists X in Z. Oh, somebody just wrote the answer for this problem. That's great. Yes, very good. For all X in Z, there exists Y in R such that X is equal to 2Y. And then somebody just wrote an answer for this that says, there exists X in Z such that for all Y in R, X is not 2Y. Yes, very good. And somebody asked, can we go over homework question? Like, I suggest that you go to office hours to talk about any specific problem that you have for homework questions, because I don't want to be writing answers out to everyone if somebody hasn't thought about the questions yet. Awesome. So this was easy, right? Okay. Next one. Oh, actually, I like this one. Let D be the set. This is the set. For the following statement, decide whether it is true or for all the elements of D. If it is not, give a counterexample. If X is greater than 5 and X is less than 7, then X is negative. Any volunteers? Any thought?
Would a counterexample be 3? Or no, never mind. It would be, actually, let me think about it for a minute. I kind of jumped the gun.
Great.
Is X in D?
X has to be in D, right? Because it says whether it is true for all the elements of D, right? So then X has to be in D.
I think it's false.
Why is it false?
Because there is no number between, first, I don't even see any negative number there. And then there's no number between 5 and 7.
Exactly. There is no number between 5 and 7. So this, right? So it's like there is no number. So like basically this can be written as P implies Q, right? So P would be this would be P, and then X is negative would be Q. If we do this, then we have the statement P implies Q. So you just said there's no number between 5 and 7, right? So that means P is false, always false. There's no chance that P is true. So it doesn't even matter. You remember with implications, it's only false when, so implication is only false when P is true and Q is false. This is the only time that the implication is false. So when P is always false, this statement is always true. So if you go back and look at the true-false table, truth table of implication, you would remember that any of the P, when P is false and Q is true, this is a true statement. When P is false, Q is false, that is also a true statement. And obviously X is not negative, so in this case, Q is also false. So false implies false is a true statement. Yes, there is. So why is P always false? Is it because there's no value between 5 and 7? Yes, that is correct. There's no value between 5 and 7. That means X can never satisfy this statement where X is greater than 5 and X is less than 7. So there's no X that satisfies that statement.
Oh, I see what you're saying. So are you saying like if there was, let's say there's 6 there, if and
so right,
does,
so you're saying that, yeah, there's like 6 right here.
yeah. So it does not
Right,
matter
so
if X is negative. Yeah.
Yes, exactly. So if there is 6 in the set, then the statement would be false, because we do have something that makes P true. So like this implication becomes true implies false, and that is a false statement. So we are out of time. If you need to leave, go ahead. And if you have any other questions, you should ask now or come to office hours. But good luck. Go ahead.
I have a question on the homework, but it's not really about the answer. It's more about converse.
Okay.
So it talked about how a triangle is an isosceles if it has 2 equal sides or 2 equal angles. But if you flip that statement, isn't it equivalent? But we learned that they're not equivalent. So
what do you mean by flipping that statement? So you're saying that, so we now have P implies Q, right? The one that you just said. And flipping the statement meaning what?
Converse, the converse.
Converse, so Q implies P.
And so in the case of, if it's an isosceles triangle, wouldn't they be equivalent?
So the thing is, like, converse is not necessarily not true. So the thing is, like, if P implies Q and Q implies P, that is an if and only if statement. So that can happen. It's not that it's always false. It's not that the converse is always false. It's just that a lot of the times, like, they're not always equivalent. Like, P implies Q does not always equal to Q implies P.
Okay, yeah, that makes sense. Thanks.
Yeah.
I had a question about one of the lecture quizzes.
Okay.
Right. So like I was just going through the answers and like what I answered. So for one of them, like I can see that the answer that I put in and the correct answer are pretty much the same, but it's still marked wrong. Like,
yeah, you can send a private message on Piazza to the instructors,
okay.
And then just take a screenshot of your answer, and then we can discuss there.
All right. Okay. Sounds good.
Yeah.
Thank you.
I just want to recap real quick, just to make sure I get it. So we already agreed that it's true, right? That the statement is true, right? The original statement.
This one? This problem?
Yes.